You hear the words work, energy, and power all the time, right? But what do they actually mean? Well, in physics, they have very specific definitions. And once you get them, you'll start to see the whole world a little differently. So let's dive in and really unpack what they mean.
All right, let's kick things off with a classic little thought experiment. Imagine you're pushing against a solid brick wall. You're pushing with all your might, you're sweating, your muscles are burning, you feel totally exhausted afterward. But in the world of physics, you've done exactly zero work. Zilch, nada. How on earth is that possible? Well, this little paradox gets right to the heart of what we're talking about today.
Okay, so what is work, really? Turns out the scientific definition is surprisingly simple. It all boils down to two key ingredients: force and movement. So here's the deal. For a physicist to say work was done, you've got to check two boxes. Number one, you apply a force to something. And number two, that something has to actually move a certain distance because of that force. If it doesn't move, it doesn't matter how hard you push. No movement means no work. It really is that black and white. And the math behind it is beautifully simple. It's just work equals force times distance. That's it. And the unit we use to measure it is the joule. This also means that pushing with a little bit of force over a really long distance can be the exact same amount of work as pushing with a ton of force over a short distance. And this comparison makes it crystal clear. On the one side, you have a car that's actually moving. A force is applied, it covers a distance, so work is absolutely being done. But on the other side, you've got that person pushing on a wall. Force is definitely being applied, but the wall's displacement is zero. It's not going anywhere. So the work done on the wall is zero. And this really sums it all up. Even if you feel tired, even if your body used up its own chemical energy, if the object you're pushing on doesn't move, then no physical work has been accomplished on it. And that, in a nutshell, is work. So if work is the action itself, then what allows that action to happen in the first place? That, my friends, brings us to energy. You can think of energy as the fuel for work. It's the stuff you need to make anything happen at all. In physics terms, energy is just the ability or the capacity to do work. It's the potential for something to happen. And for what we're talking about today, we're going to focus on two big ones: potential energy and kinetic energy. Let's start with potential energy. This is basically stored up energy. Take this engine hanging from a crane. It's not moving, but it has a huge amount of stored energy just because of its height. Gravity is pulling on it, and that energy is just waiting to be released. And the formula for it, PE equals mgh, is just a fancy way of saying its stored energy depends on its mass, the pull of gravity, and how high up it is. The other side of the coin is kinetic energy, and that is the energy of motion. You see it in this car cruising down the road. The faster it goes, or the heavier it is, the more kinetic energy it has. Now the formula, Ke equals 1/2 mv squared, might look a little intimidating, but all that v squared part really tells you is that an object's speed has a huge impact on its energy. Doubling the speed doesn't just double the energy, it quadruples it. Okay, so we have these two types of energy, potential and kinetic, but the really cool part is how they play with each other. They're governed by one of the most important fundamental rules in all of science. This is a fundamental rule of the universe, the law of conservation of energy. Think of it like the universe's most important accounting principle. Energy can't be created out of thin air, and it can't just vanish into nothing. The total amount always stays the same. It just transforms, swapping outfits from, say, potential to kinetic and back again. And this diagram, it's the absolute perfect way to see this energy swap in action. We're going to watch that stored potential energy turn into the energy of motion, kinetic energy, right before our eyes. All right, let's break this down. At the very top, at point A, the object is perfectly still. Because it's at its highest point, it's loaded with potential energy, but it's not moving, so its kinetic energy, zero. Then it starts to slide. As its height goes down, it starts losing that potential energy. But remember the rule, it can't just disappear. So what happens? It turns into kinetic energy as the object starts moving faster and faster. And finally, when it hits the bottom at point B, it's at rock bottom. Zero potential energy left, but it's flying. All that stored energy has become the energy of motion. The total amount of energy at every single point on that ramp, exactly the same. Okay, so we've got work, which is the action, and energy, which is the ability to do the action. The final piece of our puzzle is power. And power is all about one thing, speed. It's not what you do, but how fast you do it. Simply put,
Power is the rate at which you do work or use energy. Lifting a heavy box quickly requires way more power than lifting it slowly, even though the total work you do is exactly the same in both cases. And we measure it in watts. 1 watt is just 1 joule of energy being used every single second.
You know, this car analogy is probably the best way to get the difference between energy and power straight. Energy is the total amount of gas in your tank. It's how much fuel you have. Power is how fast your engine can burn that fuel to get you moving. A Ferrari has a high-power engine that burns gas like crazy, while a little hybrid has a low-power engine that sips it.
And this same idea applies to pretty much everything, especially technology. High energy density is like a big log for a fire. It holds a ton of energy and burns for hours. Your phone battery is the same. It's designed to release its energy slowly so it lasts all day. High power density is like the kindling. It doesn't have much energy stored, but it releases it all in a powerful, fast burst. Think of a camera flash, a huge blast of light in an instant. That's high power.
Okay, so why does any of this matter in your day-to-day life? Well, you actually pay for it every single month on your electricity bill. Let's make this super practical. So, you ever look at your bill and see that kWh thing? That's kilowatt hours. And here's the key. That's a unit of energy, not power. It's how much energy you'd use if you ran a 1,000-watt device for a whole hour. So let's run the numbers on a pretty typical household.
All right, we're just going to use our simple formula from before. Power is just energy divided by time. Step 1, we've got our total energy from the bill, 300 kilowatt hours. Step 2, our time. A 30-day month has 720 hours. So now, all we do is divide the energy by the time.
And what do we get? We get about 0.42 kilowatts, or 420 watts. So what does that even mean? It means that, on average, this home was using energy at the same rate as leaving 4 old-school 100-watt light bulbs on all day, every day, for the entire month.
And all this brings us back to a really interesting question for the modern world. Think about your phone. What's more important to you? High energy density, so your battery can last all day long, or high power density, so you can charge it from 0 to full in just a few minutes? Right now, we often have to choose. And finding a way to get the best of both worlds, that's one of the biggest holy grails in battery technology today.